solve. He's got numerous important publications being improved pneumonia diagnosis of radiological images using hybrid loss with conventional CNN, which is a term used in artificial intelligence. And another one based on neural structure learning. He has been assistant professor at IIT Kanpur, which is a center of excellence in AI in healthcare. And he's also associated with Advanced AI Vision Lab. He's a senior researcher with Samsung Electronics, again from South Korea. Dr. Tushar, over to you.
Thank you. Thank you. Hope you can hear me at the back. Yeah, back is always privileged because those are the world leaders and world kind of transformers. I always say in my class every time. Yeah. So they have given me a difficult task to begin the inning of a second session where we are running behind the time. When the run rate is less, everybody is hoping Sachin or Sehwag and they sent Rahul Dravid. I hope I can live up to the mark of Rahul Dravid, the greatest player that I admire. So I will introduce about some aspects AI in healthcare, which might be not trivial to you, but these are very important. Before going into these details, some of the details about myself that I usually keep like secluded or hiding from the world. These are the paradigm that we are working on. It's a cancer diagnosis from non-invasive modalities, be it larynx or epithelial lesion, also the defect and deviations, detections in the bones or different tissues from X-ray, MRI, ultrasound or fundus images. Also working on cognitive biomarkers recognition, BCI and EEG signal processing, computational pathology, also robotic manipulator, which we are working for warehouse automation, where the data set is pretty plenty. We can train the AI algorithms swiftly. And then we are moving towards the AI robotics for robotic surgery. I was working more than 5 years, almost 7 to 9 years, but I mentioned only 5 years because a couple of years overlapping with my PhD. Working with Samsung South Korea. So I spent almost 9 years in Korea. I can speak Korean. I can read, write everything in Korean. But yeah, that life and also the green card I left to come back here. They're working. I was working in wholly in AI, starting from developing a variety of products in Samsung mobile phones that you can see, the intelligent scan, also the anti-spoofing in fingerprint scanning. So these, I was leading the team, also working from ground to develop the programming. And throughout that period, I could have patents, almost 68 patents, and last 4 patents we filed from IIT Kanpur. So that's why industry is kind of running behind me. So I am kind of sought after, but somehow I ran and kind of went back to IIT Kanpur, secluded place, but I don't know how AFMC found me there and brought me here. So it's always fun to teach and be among students, which are lively every day and night. Of course, they are more lively at the night. They work a lot. So these are the work I do with my students. It's you can see image and video analysis, which is very essential for autonomous driving. Then object detection, recognition, microscopic image analysis, also the image restorations where generative adversarial networks we work on, and object tracking, also stereo vision. So why that I'm presenting here and how that is related to healthcare. So you can see the technology here we develop. It is pretty easy to get the data set for. There is no privacy concerns. There are no kind of reclusion to share the data. So there we can develop the algorithm, let's say for segmentation. If we can develop the robust algorithm, it's not difficult to transfer that algorithm for, let's say, tumor segmentation. or for fundus image, the veins or capillary segmentation from that to onwards. So we work upon that. Then core machine learning, where we also work on bioinformatics, quantitative biology, and data-driven healthcare, and the robotics, where human robot interaction as well as robotic manipulator, where we can perform a precise surgery, where micrometer range also we can have a proper drilling. So these are the works. Now moving on to the today's topic, it's AI in healthcare. That starts with more on robotics. So let's on some aspects on robotics, also how that AI buzz has been created, or is it a really buzz, or there is a groundwork behind that. So what is the state of this AI today? So let me take you through that one. So this is the current state AI I'm presenting. This is the data set that you can see. Top row, bunch of images. First kind of image is 9 images collided together. It's a mammal, then placental, carnivore, canine, then comes the dog, then comes again the working dog. Top row I am mentioning. And then last column in the top row is the husky. Then comes the second and so on. So many of us will not be able to classify that thing. Like husky, many might be knowing, but there are different types of breeds in this data set. So this data set consists of, this is the subset of this ImageNet, which is 1000 classes, where there are 1 lakh test images, validation which is needed to test or tune the parameters of the algorithm, 50,000 images, and for training 1.2 million. This is the subset. What is the large set? Large set consists of 14 million images and 21,800 classes, different classes that you have to classify, whether it belongs to a craft, a watercraft, sailing vessel, sailboat, or even a trimaran. So this fine grained classification, where do humans stand? Like at what range in that classification range? So the Stanford classmates, where they kind of perform a GUI based web platform, where they send these 1 lakh images to these graduates, Stanford graduates, and ask them to classify these labels, these 1000 classes. And error is measured. So error that comes out to be 5%. So 5% is human state of the art. That came around 2014. So that human trial is being performed. So 5% on this data set. And mind you, these are Stanford graduates, not the common man. The error might be larger if we test on like usual people. So that, and also the different distribution of data set that you can see, it's not common across. Approximately 1000 to 2000 images are present per class for those 1000 classes. Some of the class you can see sneaker, which is having only 200 images. So these are the important parameters when you want to train or you want to see a algorithm getting trained via AI. These all factors affect that. And at the end, you can see the image is pretty dark, not that good. The algorithm can easily detect different types of categories in the image, even the chair, dog, or person at the corner. And images are not pretty large. These are only 228 by 228. So 200 cross 200 small images. There it has to be detected. Now it started with algorithm, like the data set was created 2009. The competition was held in 2009. The error was around 30-35%. Then 2010, where existing algorithm, classical image processing algorithms were tried, the error rate was 28%. Then comes 2% decrement in that error, 26%. And there is a drastic change, 2012, where I was also working on the thesis on a different problem on action recognition. We were also working on these topics that time. So that AlexNet, that module, which was proposed or kind of transformed, a slightly transformed version from 1998 LeCun model. So LeCun is currently a scientist in AI. He also transferred to New York University. So he proposed when he was a graduate student with Jeffrey Hinton. So that just for simply detecting postal stamp markers, 2000 to 8000 kind of characters he tried to classify with very good accuracy. And then he kind of transferred his algorithm to IBM that time. So 1998, that proposed algorithm, just slightly modified algorithm with using new GPUs trained on same data set suddenly achieved 16% error rate, down from 26%, 10% drastic margin. That was huge kind of jump, which is pretty difficult to achieve that kind of height at that point. But you can see the algorithm which came, which is almost similar to 1998, 10 years back. Only the computational power has improved, where that kind of large data set we can train over 2 to 3 GPUs that time. And then suddenly you can see 2013, 14, that human was 5%. And finally 2015, we were able to beat that accuracy to achieve 3.6%. And up to 2017, it's 2.3%. Currently, if you see, it's like in AI community, nobody looks at that computation now. It's below 1%. It's of no of interest now. So this is the current state. You can also see 2020 to 24, almost 23 December, that different AI models are presented there. You can see 2012, where the measure is around accuracy 50%, where currently almost around 99%. And you can see there is a sudden jump around 2012 to 14. And then now it's platooning. So that's why 2016 to 17, AI buzz is getting created, because people can see the actual results on the ground. It's not like it's just the buzzword. That's why most afraid people are the industrialists, not the doctors, not the other, because their main top line is getting hampered by any other industry who is kind of venturing into AI. They are most afraid. So now moving on to the conventional diagnosis. So that was the state of the art AI. Moving on to this conversational diagnosis, you can see how doctors diagnose a patient. So they have a conversation, they see the body language, then overall perception they create in their mind, where they have trained themselves throughout the period and throughout the via textbook, via practice, and so on. Then they use few KPIs, key performing indices, like temperature, pulse rate, that the nurse has measured. They believe on that. And there is also caveat that before patient comes in, he might have taken the paracetamol, so to reduce the temperature. Also, the heart rate for athlete, it's a different heart rate than a common man. You don't know whether that person, though heavy built, is athlete or not. And fever is usually accompanied by higher pulse rate, which is not easy to hide. So now with AI, you can have that KPI any number, not only few number, even like 20, 30, 100, this kind of KPIs easily can be handled. Then correlation between the KPIs, like temperature versus heart rate, that correlation you never might have analyzed, but AI can do that for you. Also the knowledge from different diagnostic sites, also knowledge from different hospitals can be shared. That will improve you, like as a doctor, that can improve you a lot. So that knowledge transfer, it's not that easy for human to human interaction, but for AI, it's pretty easy to get that data, or even the neural network trained on two different sites can share that knowledge easily via knowledge distillation algorithms. Conversation with patients, of course, that was lacking. That can be also brought in with the voice, face, even pupillary data can be analyzed. Whether there is a pupillary dilation or contraction, that can be analyzed. And that gives very strong biomarkers to analyze. So there comes the trust. Should we trust AI? So that trustworthiness can also be achieved. So the algorithmic research has been happening from last 5 years for trustworthiness of AI. Usually it's like without trust, there is no wide acceptance, and especially in medical field or healthcare domain. So that comes the, if AI predicts something, we want AI to explain that, why you are predicting that kind of diagnosis. So that's the explainable AI. So that algorithms need to explain why these algorithms say so. So that's explainable AI. That's also a part, so that you can trust what the AI is out producing. There are different kind of modules, external variables, then perceived usefulness. So here we are, mostly the doctors, that perceived usefulness, they are seeing, some others are using. The second block there. There is a shift in attitude towards using algorithm. Also behavioral intention, and then the actual system use. So from the actual system use, we may be